All right, I hope you guys enjoyed your day off and the challenging problem of the day I gave you on your day off. Let's go over the key. All right, on the problem of the day, I gave you guys a hint. The first reaction for the problem of the day involves a strong base. So we can't forget acid-base chemistry. Acid-base chemistry is coming back next week. And in this case, we're just doing a simple proton transfer. So let's draw our starting material again. And the base we're using, I said, was sodium hydride. Sodium's always positive, which means our hydrogen is what? Negative. So just like a proton is a really strong acid, hydride is a really strong base. So now we need to identify the most acidic protons on our starting material. Where are those most acidic protons? Yeah, in one of the top corners. It doesn't matter which corner you pick, they're all equivalent. So I'm going to draw in these protons. And this hydride will reach over, grab this proton, and am I done? No, we have to break the sigma bond. So we can't forget arrow pushing with acid-base chemistry. Now we've got our intermediate. And this intermediate has a negative charge on that carbon. And what's special about this intermediate? Resonance. So we can draw a resonance structure where this lone pair delocalizes down here, kicks up a pi bond. Now we've got oxygen with the negative charge, our pi bond here, and our original hydrogen out there. And I'm going to write plus Na plus. What happened to our hydride? Yeah, it turns into hydrogen gas. So hydride, when it combines with a proton, forms a covalent bond between two hydrogen atoms. That will bubble out of solution as hydrogen gas. It's kind of a cool reaction. You know it's done when it stops bubbling, right? All right, we've got this intermediate. The intermediate, is that going to be a nucleophile or an electrophile? Nucleophile. It's got a negative charge on there. All right, then we've got our electrophile in step 2, bromomethane. So let's think about bromomethane for a second. Bromomethane must be an electrophile because we already have our nucleophile identified. Is this going to go through an SN1 or SN2 reaction? 2. If bromide fell off on its own, that would leave us with a methyl carbocation, which is incredibly unstable, right? And if we think about it doing an SN2 reaction, the backside is very accessible, right? We don't have a big bulky group sticking in the way, so we can do a backside nucleophilic attack. And this comes, attacks here, kicks off our bromine, and we get one of our products. We get CH3H plus NaBr. And how did we get our second product? Yeah, if we think about our intermediate, it's got 2 electrophilic or nucleophilic sites, one on the oxygen and then one on the carbon. Both can do a nucleophilic attack, so we can draw this going twice. And we can alkylate the oxygen. And our hydrogen's still in that same spot. Now, a lot of people were asking me, how can we predict the major versus minor product? That's a little beyond the scope of introductory organic chemistry, but if you go on and take advanced organic chemistry, you would learn a little bit more about this, but a lot of it has to do with the cation that's involved in the reaction. We're not really going to cover too much of that major versus minor product. But one thing I will say is you guys just solved a third term organic chemistry problem using the basic chemistry that we've already learned in first term. So The key is that these basic elementary reactions show up over and over and over and over again. So we've got to make sure that we understand the basic substitution principles. Does that make sense? Are there any questions? You guys are all shooting daggers at me with your eyes. Thanks for the day off problem. All right, let's go to chapter 7. When we left, yep.
So in order to have this complete, you would have to have both reciprocities like that.
I'd have to see how you wrote it out, but you should always draw both resonance structures if they're both major contributors.
This one is minor. So if in another one, if one was really minor, would you always have to draw out?
You don't have to draw really minor contributors, but it's always a good idea to draw major contributors out. I just have to see what you wrote on there. Yeah. All right, so on Tuesday when we left, we ended talking about solvents and substitution reactions. Now we're going to address the leaving groups, that last portion of our table that we need to fill out. So when are leaving groups important? For SN1 reactions or for SN2 reactions? SN1. So we can go through and we can say leaving groups are very important for SN1. And the reason is, what? Why is it more important than in an SN2? Yeah, the rate determining step involves loss of the leaving group. It's moderately important for SN2. Because it still is getting shoved off, but the nucleophile is what's doing the shoving, right? So it's not falling off on its own, it's being shoved off, so it still needs to come off. It's just not the absolute sole factor in the rate determining step. So we can write not solely responsible for rate determining step. NU is important. All right, leaving groups are a little bit more intuitive than nucleophiles, so let's take a look at some leaving groups, and I want you guys to help me pick which one's the better or worse leaving group. So leaving group comparison. All right, let's say we've got iodide versus bromide. Which one's going to be our better leaving group? Iodide. Okay, so let's circle that and we'll say, all right, this is a better leaving group. All right, let's do another one. Let's do something a little bit trickier. Actually, sorry. Which one's the better leaving group? One on the left. Okay, so we can circle our leaving group and we can say, all right, if this one falls off, it's the better leaving group. Yeah, that's $1 million question. Why? Yeah, we have to think about these in the same way we think about conjugate bases. When your leaving group falls off, is it going to be stable? That is a really important question to ask. When you're comparing this, you can basically compare them as I minus is more stable. Oh, shoot. I don't want weather. Come on.
I can tell you it's bad.
It's bad. I minus is better than Br minus. And why is iodine more stable than Br minus? It's bigger. So we're going back to our rules that we had for conjugate bases. As you increase in atomic size, you increase stability, right? So I minus is better than Br minus. Same thing with this one. We can say, all right, acetate is better than methoxide. And this is due to resonance, right? I heard somebody say resonance earlier. So when we're looking at leaving groups, we're using the exact same logic that we use for our conjugate bases, right? So let's write that down. Leaving group stability is directly related to stability of conjugate acids. Conjugate bases. All right. Now, we're going to run into a little bit of trickiness, but before we continue on into the trickiness, let's kind of make a chart. And you guys you're welcome to copy this down or just look in your textbook. But a really good leaving group is going to be a stable conjugate base. So what you can do is think of the acid that it would have had to have come from. If your leaving group is the conjugate base of a strong acid, that means it's a good leaving group. However, as soon as we get down to pKa's around water, then we start running into bad leaving groups. Why are these bad leaving groups? Yeah, they're really not that stable in terms of conjugate bases. And then what can hydroxide do? It can also act as a nucleophile, right? So we don't want our leaving group to be a nucleophile. This happens occasionally, and I'll show you guys what I mean. So let's do this example. I've got sodium iodide. So sodium is positive, iodide's negative. And I've got bromoethane. What will our hypothetical substitution product be? Yeah, the iodide could substitute theoretically with the bromine, and you'd be left with sodium bromide. Is this going to be SN1 or SN2? SN2, we've got a primary electrophile. Primary electrophiles prefer SN2 over SN1. But what we have to do is we have to compare these, our iodide to our bromide. Which one's the better nucleophile? It depends on solvent. You guys remember? So let's assume this is an aprotic solvent. Now which one's the better better nucleophile, bromide or iodide? Bromide. So our leaving group is the better nucleophile than our original nucleophile. So which way do you think this equilibrium is going to lie, the left or the right? It's going to lie on the left. So if we look at this, the equilibrium is really not going to be super favorable for the product side. The problem is our leaving group is a better nucleophile. So if you are looking at trying to make a compound and you want to do a substitution reaction, you always have to keep track of your leaving group and pay attention to the nucleophile strength and compare that to your leaving group. You don't want your leaving group to be a better nucleophile. All right. Let's take a look back at solvents, though, because we said Tuesday, that solvents matter a lot. All right. Let's recall what we covered on Tuesday. On Tuesday, we said that solvents can stabilize or destabilize nucleophiles. What about aprotic solvents? Were they helping to stabilize the anion in solution? Not a whole lot. In fact, the hydrogen bonding we said could stabilize them, but with aprotic solvents, the goal is to actually destabilize our nucleophile. We wanted to raise activation energy. So solvents can be used to stabilize or destabilize starting materials, transition states, and or products. So for example, with our nucleophiles, we said in aprotic solvents, we can destabilize our nucleophile, raise its energy, and lower that activation energy that's required. We can alternatively try to stabilize our transition state, bring that down, and then also lower the activation energy. So solvents are a really important tool that we have. And this also matters a lot for our leaving groups too. So the goal with leaving groups is to stabilize them. As they fall off. So let's think about that. Would we want to use a polar protic solvent or a polar aprotic solvent to stabilize a leaving group as it's falling off? What would be more stabilizing? Protic, right? So we said Tuesday, that hydrogen bonds stabilize anions. If we deny them hydrogen bonding, that destabilizes them. In this case, we're looking to stabilize them, so we do want hydrogen bonding. So polar protic solvents help to stabilize the leaving group as it falls off. Does this mean we want to use polar protic solvents for SN1 or SN2 reactions? SN1. Which is exactly what we said yesterday, or Tuesday. We said SN1 reactions prefer to be in polar protic solvents, SN2 reactions prefer to be in polar aprotic solvents. So let's take a look at what I mean by this by looking at our energy coordinate diagram. So I've got energy on this axis, reaction here. I've got my starting material here, and I'm going to draw just a generic SN1 starting material with our leaving group. And what will the reaction coordinate diagram look like? Two humps. It'll look like a camel. So we go up to our first transition state, down to our carbocation intermediate. And then, it'll go down to our product, right? So we've got our product right here with our nucleophile. All right, let's look at this transition state. Let's try to draw what this transition state would look like. So I want you guys to help me out by drawing this first. But what's going on in this first transition state? Yeah, so we need to show the loss of the leaving group. What's going to have the partial negative charge and what's going to have the partial positive? Yeah, the leaving group will be partial negative. So if we draw this, we've got a dash bond where our leaving group is falling off. That means our leaving group, we said, is going to be partial negative. Our carbon's going to be partial positive. And if you think about polar protic solvents, they'll want to interact with that leaving group as it's falling off, right? So let me draw solvents in green. let me slide this down a little. So if we've got a bunch of solvents around that leaving group, they can all hydrogen bond to it as it's falling off, right? So we can think about these hydrogen bonding interactions that help lower the activation energy for this leaving group. So you could have said, well, in aprotic solvents, it would have had a much higher energy pathway to overcome, but in a polar protic solvent, you're allowing that leaving group to fall off with lower energy because it's being essentially caught and stabilized by the polar protic solvents as it's being let go. Does that make sense? All right. So let's go back to our chart and fill in that last piece.
One quick question.
Yep.
Does the solvent then interfere with the nucleophile reattaching, or does it not hydrogen bond to?
That's a good question. So oftentimes what chemists do in order to prevent interference is the solvent they choose is also their nucleophile.
Okay.
Yeah, and that's a good way of avoiding any conflict between your polar protic solvent attacking in and your other nucleophile attacking in. Just only give it one option. Yeah. All right, so leaving group for SN2 reactions, we said it's moderately important. And over here, it is very important. And I'll write rate limiting. And so now we've got our full chart filled out, but we do have to tackle one other tricky aspect. So let's go back. And let's say I want to do this reaction, where I've got sodium iodide plus ethanol. And my goal is to make an alkyl halide and sodium hydroxide. Will this reaction work?
Yes.
Let's take a look again. So I'm going to actually change this into an ion pair. Let's compare our nucleophile to our leaving group. So we've got our nucleophile, which is iodide, and our leaving group, which is hydroxide. Which is the better nucleophile? The OH is. So we can go through and we can say this is a better or less stable nucleophile. Do you think this reaction is going to want to go to the product side if we're kicking off something that's a good nucleophile? No. So in this case, the reaction will not proceed since the leaving group is a better nucleophile. But let's say I really, really, really need to make iodoethane, and there's nothing I can do about it. That means we have to start developing some tools to work around this problem, right? And there's a couple tricks that chemists have available. So let's do trick number 1. Convert an OH, or an alcohol, into a OTS, and I'll describe what that means, but essentially this is called a Oscillation reaction. So I'll show you guys how this works. Let's say I've got this alcohol. What I need to do is to react it with this new reagent that we haven't seen. This is called tosyl chloride, or people abbreviate it as TSCl. So this whole portion from here over is our tosyl portion. Over here we've got our chloride portion, so it's just tosyl chloride. And when we would do this reaction, we have to use a special base. So in this reaction, we use this non-nucleophilic base. It's a heterocycle with nitrogen in the ring. This is called pyridine. People oftentimes abbreviate this PYR. So we react our alcohol with tosyl chloride and pyridine. And when we do this, we convert this alcohol into a tosyl group. We're not going to get into the mechanism, but why do you think we want to convert that alcohol into the tosyl group? Yeah, if you think about hydroxide, if it falls off, it's really, really unstable. If our tosyl group falls off, it's really, really stable due to resonance, right? It has a lot of different resonance structures that we can draw, and that makes it an excellent leaving group. So now that I've got a good leaving group, and I started with a poor leaving group, now I can do my second step of the reaction. And again, I'm going to react this with, actually let me do it on this side, sodium iodide. And will this be an SN1 or SN2 reaction? SN2. We have a primary electrophile. Primary electrophiles favor SN2. So we can say, okay, this iodide is going to now do a backside attack and kick off our leaving group. And then we're left with our tosylate salt. This is very stable. Whoop. Let me slide this over. All right. This is a really useful trick, but it's primarily used for SN2 reactions. You don't see it very often for SN1 reactions, and I'll show you guys why. So let's write this down. This is very useful for SN2 reactions. Let's look at trick number 2. So we've got trick number 1 up there. Trick number 2 is convert our alcohol into water. So let's say we're starting with our alcohol. First thing I can do is react this with hydroiodic acid. Acid-base chemistry is the fastest chemistry you will ever see. It always is faster than every other sort of reaction is possible to take place. It'll beat everything out kinetically. So what's going to be gaining the proton in this case? The oxygen. We've got 2 lone pairs on oxygen. So we can draw the oxygen getting protonated, kick off our conjugate base. So we went from what was a bad leaving group to now a good leaving group. Actually, let's add on a couple more groups to make this an SN1. All right, so we've got a good leaving group. It's attached to a tertiary carbon. what do you think will happen if we've converted that into a good leaving group? Yeah, it'll fall off on its own. So we can draw the leaving group falling off. Now we've got our stable carbocation, because it's tertiary. We've got Br minus floating around that was left over from this first step. Or sorry, I minus. Confusing my halogens. And we've got H2O. All right, why doesn't the water just attack back in? It's pretty stable. So is iodide, though. I mean, they're relatively stable nucleophiles. But let's assume we're running this in excess acid. What's the fastest reaction? Acid-base. So if we're running this in acid, this water won't even have a chance to do anything, because this water will quickly grab a proton and form hydronium. Whoops. So let's circle this and say water that was kicked off quickly gets protonated. And H3O plus is a poor nucleophile. So before that water even has a chance to attack that carbocation, it's dead in the water. It's protonated and it forms hydronium. That leaves us with our iodide. The iodide's still hanging out in solution. So our iodide can just add directly into this carbocation, and it can give us our desired product. So this is a pretty handy reaction. Why don't you think it's super handy for SN2 reactions? What do you notice about both of our potential nucleophiles?
Not very strong.
Yeah, they're not very strong. SN2 reactions, we said you have to have a pretty strong nucleophile. In this case, we're dealing with two relatively poor nucleophiles. So we normally see this technique used for SN1 reactions. So up here we said oscillation is very useful for SN2. This one is very useful for SN1 reactions. All right, so now what we're going to do is we're going to shift gears a little bit, and we're going to do an in-class activity. So I'm going to hand this out. I forgot to put it on the back table. But what we're going to do is we're going to try to pick not only reagents, but appropriate solvents for each of the transformations. And I want you to circle whether or not the reaction is SN1 or SN2. I'll bet you guys that there will be problems exactly like this. Well, not exactly, but very similar to this on your next exam. So make sure you guys are really comfortable picking out reagents and predicting whether or not it's SN1 or SN2. And I'm going to come around the room and hand these out. I would recommend working with a partner on this and try to draw the mechanism too. Don't just give the reagents, try to do the whole mechanism. Whoop. All right, first problem on the in-class activity. Let's first identify whether or not you think it should be SN1 or SN2. Raise your hand if you think SN1. Raise your hand if you think SN2. All right, let's argue with each other. Let's try to come up with rationales for both. All right, SN1 would rely on the iodine falling off first. What sort of carbocation would we get? Primary. Can we rearrange it into a tertiary carbocation? No. So in this case, it's not likely that it's going to be SN1. But let's think about SN2. If we do SN2, is the backside attack available?
Yes.
Yes. So it's most likely going to be SN2. So we can go through and we could say, all right, it's SN2. SN2, do we want to use polar protic or polar aprotic solvents? Aprotic. So does anybody remember an example of a polar aprotic solvent? Sure, acetone. Not ether. All right, so polar aprotic solvent like acetone, DMSO, acetonitrile, THF, one of those would work well. All right, and then what nucleophile do we want to use? Should we use water or sodium hydroxide? Which one would be preferable? Sodium hydroxide. If you remember, for an SN2 reaction, we need to use a strong nucleophile. That means the nucleophile should have a negative charge. In an SN1 reaction, doesn't really matter as much. You can use a neutral nucleophile. So let's use that as a guide point, but what I do want you to do is to list your nucleophile and the type of solvent that you would use for each of these. All right. Reaction number 2. Is this going to be SN1 or SN2? SN1. We're at a tertiary carbon for our electrophile. But one thing I noticed is we've got a crummy leaving group. We've got OH. How can we convert this into a good leaving group for an SN1 reaction? Protonate it. What acid should I use to protonate my alcohol? HBr. So really, we can just run this reaction straight in HBr, and it will work, right? So pretty simple. This next reaction, if you notice, we've swapped out our bromine for this new nucleophile. And what do you notice about the stereocenter? It's inverted. Does that mean it's SN1 or SN2? SN2. All right. So it's SN2. We want a polar aprotic solvent. Okay. So let's write that down. Polar aprotic. What nucleophile should we use? Well, we can go over here and we should say, well, we're just attaching this guy on. So we could use acetate. And Daniel was asking me about this. He said, can we just buy a bottle of acetate or just write down acetate? You always want to include a cation, because anytime you have a salt, you have to have a cation-anion pair. So let's just tack on a sodium and say sodium acetate in a polar aprotic solvent. All right, next one. Next one, we've got hydroxide, and we're trying to convert that to an iodide. Is this going to be SN1 or SN2? SN2. It's a primary electrophile, but again, we're stuck with a crummy leaving group. What should we do with an SN2 reaction when we want to convert it to a good leaving group? Yeah, tosyl chloride and pyridine first. So I'll write TSCl and then PYR, just to save some time. And then step 2, what reagent should I use? We've converted our alcohol into an excellent leaving group, but we haven't substituted it yet. Let's do sodium iodide. We need I-. We want a stronger nucleophile in this case. We don't need to protonate anything. So we'll just use sodium iodide and polar aprotic. All right, and then what do you think about the last one? Is it SN1 or SN2? SN2, we have an inversion of stereochemistry. So should we use HBr here? No, if we did HBr, we would scramble the stereochemistry. We only want our inverted product. We don't want two different products out. So in this case, again, we could use tosyl chloride, pyridine. And then what about our second step? Yeah, sodium bromide and polar aprotic. All right, over the weekend, please, please, please finish up Chapter 7 on sapling. Chapter 8's pretty difficult. You need to make sure that you've got Chapter 7 buckled down before we get into Chapter 8. Please make sure you finish up Chapter 7. We do not have a quiz on Monday.